All right, so last time I showed you a little bit of this thing that we're going to give a name to called the difference quotient. We're talking about the difference between average rate of change and instantaneous rate of change, okay? This thing, this expression that you see here is called the difference quotient. I don't know if this is why it's called that, but on the top of the fraction there's a difference, and the whole thing is a fraction, which is a quotient. So I assume that's where the name came from. It's not really important that you recognize the name difference quotient, but that you're going to see a lot of these things where you have an H in there, you sometimes have an X, and sometimes you're going to add on a limit statement to that. And the idea is that we're moving from an average rate of change to an instantaneous rate of change. And that's why I did try to spend time demonstrating the conceptual difference between average rate of change and instantaneous rate of change. These are things that take time for them to settle in. So if you're still confused on that, that's fair, but you can always go back and watch those videos if you still have questions about what is the instantaneous rate of change, what is the average rate of change. What calculus classes often do, and pre-calculus classes, is they get focused on the technical stuff without really spending much time drawing to the surface the conceptual part. And so we're now going into the technical stuff, but it is even more important that you understand the conceptual idea of it. So let's say we have a function like f of x is equal to 2x squared. What does that look like? Well, it looks like a parabola, okay? What is the instantaneous rate of change? Well, the instantaneous rate of change is the slope of the line that is tangent to that curve. Tangent meaning it touches that curve at one point, okay? So the slope, the rise over the run, or the delta x, delta y over delta x. What's the slope of that line? Okay, well, what it is, what calculus will say this is they'll put a little dash in there that says f prime of 2. That f prime of 2 means what is the slope of that function at 2? And that's where the difference quotient comes in. Well, this is f of 2 plus h minus f of 2 divided by h, okay? This distance right here, 2 to 2 plus h, would be if you calculated an average rate of change. So I could calculate the slope between these two things. The instantaneous rate of change is the concept of what is the limit as h approaches 0, okay? As you get from drawing a line that goes through 2 points of the curve to one that goes through just one and is tangent at that point, okay? So that's the conceptual part. Now we're going to get into the technical part. In order to evaluate this, you need to evaluate, I think it helps to just evaluate the pieces first. What's f of 2 plus h? Well, that's going to be 2 times, and I'm putting this expression 2 plus h, I'm putting that in for the x, and they call that the argument in the function. What is that going to be? This is 2 times 4 plus 4h plus h squared, which is equal to 8 plus 8h plus 2h squared. And so what's f of 2? That's 2 times 2 squared. And that is 8. Oh, by the way, you can't just plug in when in this expression, it would be nice if you could just plug in 0 for h. But if you plug in 0 for h, what are you going to get? You're going to get 8 minus 8 over 0, which means you're going to get 0 over 0, which is undetermined, which is why we have to do some legwork to figure out if this limit exists, okay? So now I want the limit as h approaches 0 of f of 2 plus h, which is 8 plus 8h plus 2h squared, minus f of 2, which is 8. And I want that divided by h. What you'll notice happens with these, which is convenient, is the things that don't have an h in them, they knock each other out. And that's convenient because we're going to end up with kind of the same process in all these where I'm going to factor an h out of the top. So now I get h times 8 plus 2h divided by h. Okay? And now I cancel those, and I get limit as h approaches 0 is equal to 8. And what does that mean? And by the way, it's 8 because I can now plug in the 0 for h. And now I get 8. I don't get an indeterminate answer. I get just 8. And what does that mean? That means the slope of this line of the curve 2x squared at the point 2, this rise over run is 8. And that's an important concept because oftentimes in the real world, you're looking for rates of change. If you start looking for how often we talk about change, we're pretty much always talking about change. It's a change is constant, okay? Calculus is what allows you to quantify rates of change, which do allow you to understand the world, how the world works, okay? This is an example of just a basic function, 2x squared at the point 2, okay? You can get more abstract with these. Abstract is like when you use fewer numbers and more letters, okay? So let's say I have f of x is equal to 3x squared. And I want to know what's f prime of x is equal to. Well, okay, 3x squared looks like a parabola too, but if I don't put in a point, then if I keep this as an expression, what I'm going to be able to do is find a function that will give me the instantaneous rate of change at any point along that curve. That is helpful. So this is going to be f of x plus h minus f of x divided by h. Okay? Now, we can do the same thing. F of x plus h equals 3 times x plus h squared, which is equal to 3 times x squared plus 2xh plus h squared, which is equal to 3x squared, 6xh, 3h squared. F of x is equal to 3x squared. If I plug in 0 into this function right here, I'm going to get, let's go with a different, 0 over 0, which is indeterminate. It means I got to keep going. So now if I set this up, I get the limit as h approaches 0 of 3x squared plus 6xh plus 3h squared minus 3x squared divided by h. And now I cancel out the 3x squared and I cancel out the 3x squareds, and I get h times 6x plus 3h divided by h. And now I cancel out the h's, and I get the limit as h approaches 0 of 6x plus 3h. And then the 3h, when I plug 0 in for h, that term disappears, which equals 6x. Which means now that I've left it abstract. And what I mean by that, the first time when I did this, I plugged in a number and I was looking for the tangent to the curve at a specific point. That number was 2. This second time I've done it, I've kept it abstract. X represents a variable. At the end, I end up with an expression with an X in it, which means if I want to now use this expression to find the instantaneous rate of change at any point, let's say I want to find f prime of 3, that's going to equal 6 times x, which is 6 times 3, which is 18, which means if I found the slope at 3, I would get a slope of 18. If I want to say, what's f prime of 0? Well, what should we get? F prime of 0 is that's where the vertex of that parabola is. The tangent to the curve there is flat. It has a slope of 0. F prime of 0 is equal to 0. What if I do f prime of negative 2? What should I get? Well, at negative 2, it's negative, and it's not quite as steep as it is at 3. So 3 times negative 2 is equal to negative 6. Okay, so that's the idea of this difference quotient. It gives you a lot of information, and it's tedious. This is one of those things that calculus teachers do to their students at the beginning of the year, every single year. We do it because it was done to us, and there's going to be a shorter way that you learn after a while, but you have to get good at this algebraic manipulation in order to be able to solve the problems that you're going to see coming up.